Hey guys, welcome back. Houston Math Prep here. In this video, we're going to continue our discussion about the rational roots theorem by talking about how we can use our list of possible rational roots combined with synthetic division to find which of those possibilities actually are roots of our polynomial. So recall that a value is a zero or a root of a polynomial if when we use that root and do synthetic division, we get a remainder of 0. So using this concept, we can see here that x minus 2 is a factor of x cubed plus 2x squared minus 5x minus 6. So this one is a factor, or we could say 2 is a root because we got 0 as a remainder. Whereas if we use 1, we get a remainder of -8. So this one is not a factor or not a root. So let's see this in practice. So here we're going to take this h of x polynomial, this cubic polynomial that is in standard form. We're going to list out all the possible rational roots. So we're going to make our list of plus or minus p over q, and then we're going to use synthetic division to start testing each one of those roots so that we can take this polynomial and get it into a completely factored form. So let's begin by listing out our possible rational zeros. Again, our rational roots theorem says we're going to get those possibilities by taking plus or minus p over q. P is going to give us a list of all possible factors of our constant, in this case 6. So that would be plus or minus 1, 2, 3, and 6. Those are all the whole numbers that divide evenly into 6. And on the bottom of that, we'll take all the factors of our lead coefficient, which is our q. So the only ways to get 2 are 1 times 2. So expanding those out, putting each value in the numerator over each value in the denominator, we get the list 1, 2, 3, 6 from each of them over 1. And then 1/2, 2 halves is already 1, 3 halves, and 6 halves is already 3. So here's our list of potential rational zeros. So this is the list that we're going to pick from as we start testing values to see if they are roots or not. So I'm going to go ahead and set up for synthetic division to start testing. To do that, I'm going to take my coefficients, so 2, -2, -10, and -6, and I'm just going to start testing values here. So I'm going to start with +1 and just go in order. So 1 times 2 is 2, -2 plus 2 is 0. 1 times 0 is 0, -10 plus 0 is -10. 1 times -10 is -10, and -6 plus -10 is -16, which is our remainder. Since that is not 0, I know that 1 is not a root of my polynomial. So I'll repeat that process, moving on to another value in my list. So let's go ahead and move on to -1. So -1 times 2 is -2. -2 plus -2 is -4. -1 times -4 is +4. And -10 plus 4 is -6. -1 times -6 is +6. And -6 plus 6 is 0. So here we got a 0 remainder. That means that -1 is a root of our polynomial. That also means that we're ready to start writing h of x in factored form. If -1 is a root, then the factor that goes with that will be in the form x minus that root. So x minus -1 looks like x plus 1. And h of x can be written as x plus 1 times what we got here. So -6 will be our constant, -4 will be our coefficient of x, and 2 will be our coefficient of x squared. So that will be 2x squared minus 4x minus 6. Now, we want to factor this completely. Once we get down to a quadratic, 2x squared minus 4x minus 6, while yes, I can keep testing other values to see if they work, like 2 and -2, 3 and -3, and so on, I already know how to factor a quadratic. So I can use those skills to finish up my factoring. The first thing that I notice is everything in my quadratic has a factor of 2. So I'm going to go ahead and pull that out to the front, keep my x plus 1 factor, and now my quadratic is x squared minus 2x minus 3. So that will be 2 times x plus 1 times, I need values that multiply to give -3, but add to give -2. So that would be +1 and -3. Now we can leave our answer like that, or if we're going to go graphing, we might find that we'd like to go ahead and write x plus 1 times x plus 1 as x plus 1 squared times x minus 3. So here's our fully factored form of h of x, a cubic polynomial. All right, guys, that does it for this example video using the rational roots theorem. If you want to see more, catch the next video.